Hello and welcome to the course Climate Hazards and Disaster Mitigation. Today we are conducting a hands-on session on flood frequency analysis using univariate and bivariate approaches. So last time we reviewed the fundamentals of univariate flood frequency analysis. We also covered some probability concepts, how distribution fitting works, and classical flood frequency analysis methods. We also discussed the concepts of compound extremes and compound flood events. We revisited what is the need for performing a multivariate FFA. We introduced to the copula based modeling, which is a very powerful tool to represent the dependence between the flood variables. So today we are going to perform a distribution fitting exercise. We'll conduct annual maxima series based FFA using Gumbel's method. We'll estimate the dependence using correlation measures like Pearson, Spearman and Kendall-Stowe. We'll explore the MVCAT toolbox to fit copulas, and then we'll generate joint probability and return period figures to visualize how bivariate flood risk can be estimated. So starting with, this is a sample data which we have. So I'll also show the sample files. So we have two columns. First column is the year and second column is the peak discharge. So we have 1977 to 2019. That is a fairly long data, 40 plus years. And now we have already introduced you to MATLAB Online. So we'll be going to MATLAB Online. So in MATLAB Online, you click on apps. So once you click on apps, you will get all kinds of apps, and we have to select the distribution fitter app. So we'll again do the hands-on. Then what is the next step? Next step is you load the input data. Once you load the input data, then in the distribution fitter app, these kind of box will open where we have to load the stream flow data. Then we have to select the data set. Our data set is stream flow. Once we select the data set, then we click on create so that we can create that particular data set. Now once the data set is created, so you can see this is a button. It will activate when you select the data set, and it will create the data set. You can visualize the data set like this. So you can see this is a histogram of the data set. So in this histogram, now what are the options in distribution fitter toolbox? You can have new fit, you can manage fits, you can evaluate as well and exclude. We'll be mainly using new fit and manage fit to see how distribution fitting is performed. So by looking to the data, you can see that it is not a Gaussian distribution, it is a non-normal, because you can see it is skewed to the left. So now let us click on new fit. So you can rename the fit name. That is, if I'm using generalized extreme value, I'll name it as GV. This is your data, and it will show the parameters. It has shape parameter, sigma, that is scale parameter, and location parameter. Once you click on apply, it will compute all the parameters. What are your so these are the parameter values, and associated are the standard error of estimate. So we are only interested in the parameter values. So that is K, sigma and mu. Then you can create multiple fits like we did for GV. You can take another fit. So this is how the GV appears. So you can see how well it fits the model. So you can also check the fit other parameters to check how well it fits. Then you can have multiple distributions like log normal or gamma to just check that how well they fit. So the best fit distribution can be taken forward and perform the flood frequency analysis. So this is a PDF. You can also visualize the CDF, that is cumulative distribution function. So CDF will also give you an idea that how the distribution fitting helps. So with this, let us perform the same in the MATLAB. So before that, I'll just show you the data. So the data we are providing that is in Excel format. So you have two sheets. Sheet 1 has two columns. The first column is the year and second column is the peak discharge. Sheet 2 has three columns. So first two columns remain same as the previous sheet. There is a third column which is flood volume in meter cubes that is being added. So this will be using for the bivariate analysis, and sheet 1 will be using for the univariate analysis. Now let us go to the MATLAB. So as shown from the apps, you can see the distribution fitting toolbox is just here. I'll click on it and I have the distribution fitting toolbox. So sometimes it takes processing time, so that is why here it is shown busy. So this is the toolbox, how it looks like. Now I need to load the data, so I do not have the data. So let me go to the command and let me go to the slide and copy the command. So let us say I take one by one. So first I'll write the file name. So this I can do in the command window itself. I'll paste and I'll put enter. So this is the file name. Now you can see that there is an error in it. If we process it further, I'll show you that what error it shows. Let me just process it. So you can see it is showing an error, unable to open the file. Now why it is showing an error? Because you can see that here there is an extra space. So once this is an extra space, that file name, it is not the correct path, and that is why it will show the error. So let me rectify it. So I am just giving a backspace, enter, and so you can see now the code has run without any error, and whatever data, so this is my data, I can visualize my data here. So this is sheet 1, sheet 2, and if I just want to take sheet 1, so I've taken the second column. So the second column is the peak values of discharge. So you can see that is my stream flow data. So with this data, let us open the distribution fitting toolbox. Let me load the data. I will select the data as stream flow, that is my variable name, and it will give you a preview of the data. Now let us create a data set. So once I create the data set, it will appear. I can click on close. So this is my data set, how it looks like. Now I want to perform distribution fitting. I'll click on new fit. So another box will be opened. Let us say we try with a normal distribution first, just to check how normal distribution works. So there are two parameters, mu and sigma. I'll just click on apply, and you can see that the normal distribution is appearing something like this. So it is not able to capture these part of the data. So now when you click manage fits, you can have more fit. So let me go to new fit. So I create another fit. Now I take another, that is log normal. So ln2. So this is from here distribution. I'll select the log normal. So it is here log normal. Again it has two parameters, log location and log scale. I just apply it, and you can see that it is fitting better compared to the normal distribution. So you can see all the parameters. So this is a log likelihood value. You have the mu and sigma values. So based on the log likelihood value, you can select which is the best fit distribution. Let me have another fit. This time I take extreme value EV. So here this is extreme value. So this is a two parameter. So that is a Gumbel's distribution. You have mu and sigma. You do not have the third, that is a shape parameter. I click on apply, and you can see the extreme value. So extreme value is not doing properly for this. And let me take another one, and this will be my GEV. So from here I'll select the generalized extreme value. It has again three parameters. I'll click on apply, and here it comes. So you can see that GEV and log normal 2 are almost closer. Now how to select which is the best fit distribution? So you have been given the log likelihood values. So the largest of log likelihood values you can select. So minus 362 is larger than minus 363, and you can select log normal distribution to model this particular time series. However, if you use GEV, you will get little comparable results. So you can always check by putting the parameters into a flood frequency analysis module. So this is how you can explore different fits. Now this is the PDF. If I want CDF, I'll just click here from the display type, and I'll get a CDF visualization of the same. So you can see that EV and normal are offbeat, while LN2 and GV are more closest to the stream flow data. So this is all about the distribution fitter app. So let us move ahead. So if you want, you can save this session and later retrieve also. So let us now understand the next aspect. So we'll do flood frequency using Gumbel's method. So we've already discussed the aspects of flood frequency. So first is you need to estimate the parameters. Once you estimate the parameters, you calculate the return periods and then you plot the FFA curves. So what we are doing here, we are reading the data. So we are reading, so this is a file name, so the source will be different every time you input the data. Please check what is the source. So you have to provide proper path of the data. So the first column will be year and second column will be your discharge if you are using sheet 1. Now to estimate GV parameters, there is a command in MATLAB, that is PARMHAT, that is equal to GV fit of Q. So in that, the first value, it will be a matrix where the first value will be the K, that is the shape parameter, second is sigma, the scale parameter, and third mu, the location parameter. So 3 parameters you will get. Now let us print those parameters. So all the parameters we can print on the screen, so we can see the parameter values. Then you specify the return periods, for what return periods you want to compute, and then we can put in it. So once you put in return periods, you have to calculate the non-exceedance probability, that is F equal to 1 minus 1 by T. So your non-exceedance probability is 1 minus 1 by T, and using that you calculate the flood quantiles for different return periods. So this flood quantiles you are well aware, xt equal to x bar plus kt sigma. So this is how you can calculate. So you have all the values. So we will use a GV inverse function. So instead of GV, it was log normal a best fit. So for that also you can get inbuilt functions and you can see how it works. So you will have the non-exceedance probability, you will have the parameters. Once you have that, it will compute the QT values. Then you can save the values in an Excel file, and that Excel file can be used later for different purposes. And then you can also prepare the figure. So I can have a line plot, and the line plot will give me this flood frequency curve. So it will be plotted against flood magnitude in meter cube per second versus return period in years, and you can get the idea. So if you have another distribution, let us say this is for GV, and if you plot for log normal, you can compare that as well. So both the curves can be compared. So let us perform this exercise in MATLAB. So in MATLAB we have the code, which will be providing to you the code for Gumbels. So as I mentioned, you have to check what are the file names. So that has to be very carefully checked. What are the output values, that also you have to check. So I'll delete this file so that there is no duplicacy, and then you can prepare the plots. So one way in MATLAB is you run the file by selection. So I'll go step by step. So I'm selecting this and pressing F9. So let us execute this MATLAB code to understand. So we have already provided a MATLAB file gumbels.m, and along with that there is an input file which is an XLS file, week 4 hands-on.xls. So you can see this Excel file is there. So in the first sheet of the file, so we will once run the initial part and see what data we have. So I'm running the initial part of the code. So here we can see A is our data variable. So the first column is the year and second column is your flow value. So using this annual maximum discharge series, let us calculate the parameters for the Gumbel distribution. For Gumbel distribution, we'll use the GV fit command in MATLAB. So using those command, we'll get 3 parameters, that is location parameter, spread parameter, and the shape parameter. So now having calculated the parameter, I can also print these parameters on the screen. So just to give an idea how it looks like, so my shape parameter is that is k 0.62, scale parameter is 683.6, and my location parameter is 842. So it is a 3 parameter distribution, so we are fitting a GEV distribution. So if the shape parameter value is 0, then it becomes a 2 parameter, that is Gumbel's distribution. Now once the parameters are estimated for the given distribution, then we will compute the return levels corresponding to 2, 5, 10, 25, 15, 100 year return period. You can take any return period depending upon the intended use. For example, if you want to design a structure for 25 year return period, you can take that particular value. So let us run this part of the code. So here we can see QT will give us the flood quantile. So let us, so this is for a 2 year return period, it is close to 1123 meter cube per second, and for 100 year return period it is close to 19,000 meter cube per second. So this is the variation of QT, that is the flood quantiles you will get for various return periods. You can also save this output file in an Excel file. So if you want just XLS write, and you know that file as return levels will be saved here. So this particular data can be saved, output can be saved, and finally you can plot this figure to visualize how the flood frequency curve would look like. So you can see your FFA curve. So it is of this characteristic where it will give you that for close to 100 year return period, the discharge is very near to 20,000 meter cube per second. So for any return level, you can simply interpolate in between, and if you require, you can have for higher return periods as well. So this FFA curve is very useful in hydrologic analysis and design. So let us continue further. After this, we go on and explore the dependence and correlation measures. So in this particular exercise, the first part is same, that we are importing the data. However, now data has 3 sheets. That is the first, the data has 3 columns. So in sheet 2 we will refer this data. So first column is your year, second column would be your peak value, third column would be your volume value, and we will just find what is the dependence between them. As discussed in the theoretical part, we have different dependence measures. So we will first begin with the Pearson dependence. So the syntax is RP, PP, that is core, CORR. You have the variables X and Y, and type is Pearson. So we'll estimate the Pearson relationship and then we'll print it on the screen. The next we'll go for a Spearman rank, because Spearman rank will give us the monotonic relationship and it also accounts for the non-linearity. So we'll go, the only change in the syntax is instead of Pearson we'll have Spearman. And third, Kendall. So Kendall is based on the concordant and discordant pairs. So again it is a very robust measure. So we'll just replace the type and we get the Kendall tau correlation. And using a scatter plot, we can visualize what is the X versus Y variation. So let us execute the MATLAB code. So the MATLAB file correlation.m is provided to you. Since you are already having some data in the file, it is always advisable to clear that data before proceeding ahead so that there is no overwrite in the variables. Now let us input the data and visualize the data structure. So here is our data. So our data file, as I discussed earlier, first column is your year, then you have peak flow, and then you have volume of flow. So our aim is to find the dependence between peak flow and volume at a given gauging site. So first we are running the Pearson correlation. We'll print it on the screen. So the Pearson correlation value is 0.907 and the p value is very less, that is less than 0.05. That means this is a significant correlation between peak and volume. Coming to the Spearman. So the Spearman correlation, it is coming on the slightly higher side, 0.944, and again it is statistically significant. And lastly the Kendall's tau. So the Kendall's tau is 0.807 and still it is statistically significant, because all these 3 correlation measures are based on different premise, so that is why they will yield different values. In few circumstances they will yield similar values also, depending upon the nature of the data. And lastly we plot them, and upon plotting you will have a scatter plot, which you can see if you run a best fit line here, the the agreement is very high. So that is what is observed in this particular case. So moving ahead, so this is your best fit line, which will look like this, and that is why the correlation values are high. So these a few values, these are tend to deflate the correlation. So if you remove these values and rerun the code, you will get much improved correlation estimate because of these values which are very away from the best fit line. Moving ahead, we move on to the last part where we will be discussing how to fit a copula for joint dependency analysis. So for that we will first go to this multivariate copula analysis toolbox, that is called MVCAT toolbox. So just type MVCAT on Google, you will have this particular link, and below it there is a paper by Sadegh et al, which has given a very detailed elaboration on how to use this tool, and some applications are also demonstrated. So we'll use this tool MVCAT. So when you click it, it will take you to this MATLAB window, and just click open in MATLAB online. So once you click it, it will be accessible in MATLAB online. Then this folder will be displayed where you will have all the components of the code, and when you open it, you click on run mvcat GUI.m so that the GUI will pop up. So when you click it, this screen will appear, and just click on the run command and the GUI will appear. So if it is asking, then you can just add to path if this command prompts up, and then you are ready to go. So this is how the GUI appears for this MVCAT toolbox. So there are different components. So first component is browsing the data. You can either use inbuilt data just for practice, or you can add more data. There are different types of copulas, so around 27 copulas are given. So whichever are required you can try, because if you go for all 27, it will take a lot of time for the code to run. Then you can select which parameter estimation method I should go. It should be a local optimization, or it should be a local optimization plus Monte Carlo simulations. Then you run the simulation, and these types of graphs will be created and a summary will be generated. It will also give you what are the best fit distribution based on 3 criteria: maximum likelihood, AIC as well as BIC criteria. So we can use the sample data. If you open the data folder, in that data.txt is there. You can just add it. I can select any one copula, for example Clayton or Frank, and then I can produce. So once you are running the code, this type of message will pop up very frequently because it will take some time depending upon the system configuration. So you have to be patient while the code is running. And once the simulations are run, then you can see the results. They are stored in the results folder. So all fit.dst.m, and then MVCAT results are there. The summary report is there, which will give you copula rankings and the parameter values, which can be later used. Also different figures will be generated. So the figure shows the bivariate distribution for a given copula. So this is the copula which they have chosen. So this is variable 1 and variable 2. So these are the marginals, and this will give you the joint probability distribution between the two variables. Also we have the best fit ranking, that which is the best fit at 1, 2, 3, 4, 5 and so on. So these results are also available. It also gives you the dependency analysis in the text file. There was a Candles, rank, Spearman and Pearson. That values also will be provided. Okay, so let us have this exercise on MATLAB. So in MATLAB, as I indicated, I'll directly open this folder and we'll run the MVCAT GUI. So let us see. So I'm adding it to path, and this is my GUI which is here. So now let us browse the data. So this is the MVCAT toolbox I'm having. So in this I'll go to data and I'll take data.txt. So you can take other data, that is data 2 is also available. So I'll just open. So my data is now loaded. I'll select any one, let us say select the Clayton copula. If I take all, it will take too much time. I'll use local optimization method, or I can go for local optimization and Monte Carlo simulation as well. I want to include the probability lines, yes, and I'll click on run simulations. So let us see how much time it takes. So you can see on the right side of the screen this message is popping up that it is estimating parameters for the Clayton copula. So we'll just wait for some time till the results are generated. So this message is popping up that it is plotting copulas, please wait for some time. So let us wait for the results to be there. The usefulness of copula is much when you want to analyze the joint dependencies, because many a times two variables are correlated. If we analyze only one, we miss out on their joint behavior, which is very important. For example, if you are analyzing flood peak and flood volume, it may happen that the peak is small but the volume may be high, and that can lead to a devastating effect, or vice versa. So you can see for Clayton copula, this is the marginal distributions. These are the iso lines which are plotted. So you can see very clearly the iso lines and their probability, that is probability of x greater than x, y greater than y. So this is a probability being plotted. So you can see this is a return period, so they are inverse of probability. So for 2, 5, 10, 25, 50 and 100 year return period, so you can see this particular value that is falling between 25 and 50 year return period for joint, let us assume these variables are peak and volume, then the value falls here. So we can see that that is a very critical event. All these events on the left side of the curve, they are less critical because they are having return period less than 2. So this is how we need to interpret these figures. Again, it gives for the other case x less than x, y less than y, and these are the marginal distributions, how the fitted and empirical distribution works, the QQ plot. Now let us see if the summary files are also generated. So we can check the summary files. So you can see here the results file are generated. So if I open, my summary report would look something like this. I'll get the Candle rank, Spearman rank, Pearson moment correlation. What is the marginal distribution? So normal distribution, the marginal distribution for both the variables. The parameter values are given. That is, it is a 2-parameter distribution. So you have mu and sigma values which are provided. Then we can also select the copulas. So based on that, the copula parameters are provided. So you can see for the given copula, these are the copula parameters. So this is how you can perform the bivariate distribution analysis. So that's all for today. Thank you for your attention. In the next lecture, we'll discuss urban flood modeling.